Okay, so in this video, we're going to be talking about combustion analysis, and you can see the problem here that you got in class. The deal is that we have a unknown hydrocarbon, CHO, carbon, hydrogen, and oxygen, and we don't know the subscripts. We don't know the ratio of carbons to hydrogens to oxygens. But we do know that if you burn this sample, you get this grams of carbon dioxide and this many grams of water. So we know the mass of the products, and from there we're going to work backwards to see if we can figure out the moles, which are the subscripts of this hydrocarbon. So we're going to start with grams of CO2, and we're going to use the mass percent, or the percent composition of carbon in carbon dioxide. So we know that for every 1 mole of carbon dioxide, which is this many grams, there is 12.01, or 1 mole, of carbon. So we're looking first for the grams of carbon that are produced, because the grams of carbon that are in this product could have only come from one place, which is the carbon in that hydrocarbon that we put through the combustion analysis. So that comes out to 3.3738 grams of carbon, and we're going to stick with 4 decimal places for now. You'll see that in the end we're going to come up with some ratios, and it'll probably be a little cleaner. We're going to do the same thing with the water, because again, this hydrogen in the water product could have only come from this hydrocarbon. So if we can figure out grams of hydrogen, we can begin to figure out the number of moles in the hydrocarbon. So we'll start with the water, 6.073 grams of water. And we're going to use the mass percent, or percent composition, of hydrogen in water. So for every 1 mole of water, which is 18.02 grams, actually I should write 18.016 grams, we have 2.016 grams of hydrogen. Not because hydrogen is diatomic, but because there are 2 hydrogens in every water molecule. And that comes out to 6794 grams of hydrogen. So we have our grams of carbon, we have our grams of hydrogen. From here, we can find the number of moles of each by doing just a quick mole conversion. So 1 mole of carbon is 12.01 grams of carbon, and that gives us 0.2809 moles of carbon. And we'll do the same thing with the hydrogen. Notice here 1 mole of hydrogen, and we're just using a single hydrogen, because in our compound the hydrogens are not diatomic. They're not connected to each other. They're connected to other things, probably the carbons or the oxygens. So we will say that 1 mole of hydrogen is 1.008 grams of hydrogen, which gives us 0.6740 moles of hydrogen. Now what about the oxygen? Now the oxygen, we can't do the same trick, because this oxygen, the oxygen in these products could have come from the hydrocarbon, but more likely it came from the oxygen that we used for the combustion. So we can't necessarily say that these oxygens came from here, but what we can do is say, look, if we know that the sample was 6.750 grams, of that 6.750 grams, we had this much carbon and this much hydrogen. We can do a little subtraction to figure out how much oxygen is in the sample. Okay, so we're going to say the mass of the sample. Let me just move this camera. There we go. Minus the sum of the grams of carbon, 3.3738, and the hydrogen. The remainder, we're going to assume, that's a good assumption, is grams of oxygen. And if we do that, we get 2.6968 grams of oxygen, which we can turn into moles of oxygen by doing a mole conversion. And again, we're not using diatomic oxygen here. We're using 1 mole of O equals 16.00 grams of O. Because again, these oxygens in this compound, if there's more than one of them, they're not going to be connected to each other. They're going to be bonded to the carbons and or the hydrogens. So if we do that, we get 0.1686 moles of oxygen. Oops, I'm running out of room here. All right. Now, one little trick I like to do when I get to this point is just to remind myself that what I'm looking for is an empirical formula. And these moles are the ratio of moles of carbon to moles of hydrogen to moles of oxygen. But of course, this is not a good formula. We need whole number subscripts. So it's the right ratio. We just need to get to some whole numbers. So mathematically, what we would do, and I'm going to go down a little bit here on the paper, is divide through by the smallest of these numbers. So that way we get oxygen at least to 1, and we'll see what other whole numbers come out. So I'm going to divide everything by 0.1686. Oops, 1686. And when you do that, you get carbon 1.667, hydrogen, which is 3.998. We're going to call that 4, close enough to a whole number. And oxygen, of course, is 1. Now, the problem here is that this is not close enough to 2 to round it. So we have to use some fractions here. We know that 0.667 is 2/3. And if we want to get rid of thirds to get whole numbers, we would multiply this by 3. Well, if we multiply this by 3, we'd have to multiply the whole thing by 3. So we would get carbon 1.667 times 3 would be 5. Hydrogen is going to be multiplied by 3, so hydrogen will be 12. And the 1 oxygen is going to be multiplied by 3. So that is our empirical formula, which is the simplest ratio of carbon to hydrogen to oxygen you can have. You can't divide this through by anything. The second part of the problem then asks, if the compound has a molar mass of 120.15 grams per mole, what's the molecular formula? So this is the simplest ratio. It is possible to have compounds that have this ratio, but much more carbon, much more hydrogen, much more oxygen. So the best way to do that would be to say, let me see what the molar mass is of this. We can do some rough math here. 5 times 12 carbons is 60. Plus 12 hydrogens is 12. Plus 3 oxygens is 48. And that gives us 120. So really what we're saying is the molar mass is telling us that this entire thing is not just the empirical formula, but it is also the molecular formula. And there is a compound that you can find that has 5 carbons, 12 hydrogens, and 3 oxygens arranged and bonded, and that is the entire molecule. So it is, in this case, the empirical formula. It is also the molecular formula. Thanks for watching.